This conference will now be recorded.
All right, hello everyone, and welcome to the Satellite Book Club seminar series. Today's title of our talk is Lake and Sea Ice Detection using JPSS VIIRS and GOES ABI. Our presenter today is Dr. Yinghui Liu, physical scientist from the Advanced Satellite Products branch of NESDA STAR, and our facilitator today is Patrick Ide, a SU from NWS Duluth, WFO. Wanted to welcome them and look forward to hearing the presentation today. But before we begin, just a few of the routine reminders and requests. As usual, we're recording our session so folks can benefit from this talk later on. We'll have the usual Q&A, question and answer after the presentation. And we want to encourage feedback from everyone, in particular from folks from the field offices and the regional headquarters. Please post your questions in the chat room, and the facilitators and teams will field the questions from there. We ask, if you have not logged in with your full name, if you could include your full name in the chat if you have not logged in with your full name. That way we'll know who's asking the questions. That would be helpful. As usual, we're looking for future presenters, so we would welcome topics. If you have any you think you might want to present or work with others to present, please contact the TOWRS team. And the training team can help create training materials that might currently be unavailable. Please contact Brian Mata for information or questions related to that. Thanks as usual to the TOWRS team, Office of OBS, Kashad Bowman in particular, Office of the Chief Learning Officer, Satellite Programs, GOESAR, JPSS, and to our facilitator, Patrick. Yinghui, we're going to ask you to get started in just a second, but before we do, we just wanted to say a few words, let everyone know a little bit more about your background. Before joining NOAA in 2019, Yinghui was a research scientist at CIMSS, Wisconsin, where he supported a number of NOAA projects. Yinghui received his Ph.D. degree in atmospheric sciences from the University of Madison, Wisconsin back in 2006. Besides developing retrieval algorithms, he's also interested in studying trends in polar clouds, sea ice, surface and atmospheric radiation, and the atmosphere/sea ice-ocean interactions. Yinghui, welcome to the Satellite Book Club. We're ready for you to begin as soon as you're ready.
Great, thank you very much for your introduction. And also thanks very much for the opportunity to present our work on ice detection and ice concentration from JPSS VIIRS and GOESAR ABI. My name is Yinghui Liu, and I'm from NOAA NESDA's Center for Satellite Applications and Research STAR. So first, I would like to acknowledge my co-authors, Jeff Key of NOAA NESDA STAR and Rich Dwork from Cooperative Institute for Meteorological Satellite Studies, CIMSS, at UW-Madison. And I also want to thank Tim Schmidt from NOAA NESDA STAR and Lee Baylor of TOWRS team for their contributions to the slides. Next, please. Can you hit one more time? Thanks. Information on snow and ice is important for shipping, weather forecasting, and climate monitoring. Historically, snow and ice properties has been measured using relatively low-resolution, space-based passive microwave data. At STAR, besides those traditional products from passive microwave, the cryosphere team led by Dr. Key implemented algorithms to retrieve snow and ice properties using satellite imageries in the visible and infrared spectrum like JPSS VIIRS and GOESAR ABI. So far, we have implemented algorithms and routinely generate products on sea and lake ice and snow. And in the future, we will explore other capabilities if possible, like the ice sheets and the shelves and the glaciers. Next, please. This slide provides a list of all the operational and experimental products we are currently generating and exploring. So besides the passive microwave products, we are generating ice products, including ice cover, ice concentration, ice surface temperature, ice motion, and ice thickness. For snow products, we generate snow cover and the fraction snow cover product using VIIRS and ABI. And we are also exploring blended snow and ice products by combining products from VIIRS, ABI, and the passive microwave. Today, I will focus on the ice cover and ice concentration products from VIIRS and ABI. Next, please. So first, I want to introduce the definition of ice cover and ice concentration. For ice cover, it is the location of ice over inland lakes, rivers, and ocean waters. Ice concentration is a fraction, either in percentages or tenths of the ice for those ice-covered pixels. So the satellite ice cover and ice concentration products are to identify whether a satellite pixel is ice covered or not. If it's ice covered, the ice concentration is to retrieve the fraction of the ice for those ice covered pixels. Next, please. For the JPSS VIIRS and GOES-R ABI ice detection, we use a group criteria detection algorithm. During the day, the algorithm is based on that snow and ice have high reflectance in the visible spectrum and low reflectance in the shortwave infrared spectrum. And the snow and ice temperatures are lower than the snow-ice melting point. So in the daytime, a satellite pixel is identified as ice-covered if the normalized difference snow index, NDSI, is larger than the set threshold. Reflectance at 0.80 micrometer channel larger than the set threshold, and the surface temperature is lower than the melt point. So during the night, there is no visible information, so a pixel is identified as ice-covered if the temperature is lower than the melt point. For the ice surface temperature, it is calculated using a linear regression equation on the bottom figure shows. So next, please. For the ice concentration of any given ice-covered pixel, it is calculated using a tie point algorithm as shown in the equation on the top. So reflectances during the day and the surface temperatures during the night of 100% ice and 100% water are needed for the calculation. These values are referred as tie points, indicated as BS and B water in the equation. So for a given pixel, if we know the tie points and observe the reflectance or temperature of that pixel, we can derive the ice concentration by linear interpolation using the equation on the top. So the water tie points are parameterized, and the ice tie points are determined using 4 steps listed in the middle of the slide. So the first step is to select a search window with the center being the pixel of interest. So the second step is to calculate the probability density distribution of the reflectance or temperature of the ice-covered pixels in the search window. The third step is to determine the ice tie point as the reflectance or temperature with the maximum PDF. So the fourth step is to calculate the ice concentration using the equation on the top with the tie points and the observed reflectance or temperature. So we repeat these steps to get all the ice concentration retrievals for a field of view. So if you look at the figures on the bottom, they show a validation case of the calculated VIIRS ice concentration using derived ice concentration from Landsat 8, which has very high spatial resolution of 50 meters. So the derived products from both Landsat 8 and VIIRS agree with each other really well. So next, please. This slide shows the VIIRS and ABI sensor data, derived products, and ancillary data as inputs of the ice cover and ice concentration algorithms. We want to emphasize that the VIIRS and ABI ice cover and ice concentration are only for clear sky pixels. So the quality of the cloud mask is very important to our products. So next, please. So the JPSS satellite orbits the polar regions 14 times a day. So the VIIRS swath width is 3,000 kilometers. So of the VIIRS 22 bands, there are 5 high-resolution imagery bands, the I bands, with 375 meter spatial resolution at nadir. There are 16 moderate resolution bands, M bands, with 750 meter spatial resolution. So these two animations show the VIIRS overpasses during a day in the Arctic for one shortwave infrared channel, which is 1.61 micrometer, and one infrared channel, which is 11 micrometer channel. So next, please. So this slide is the same as previous one, just showing the VIIRS overpasses in the Antarctic during a day. So for both a 1.61 micron reflectance and 11 micron brightness temperature. So next, please. So with the wide spatial coverage, high temporal frequency in the polar regions, and also the high spatial resolution, the derived VIIRS ice cover and ice concentration provide a complete coverage of the polar regions with very high spatial resolution up to 375 meters. So this slide shows the derived VIIRS ice concentration for all the overpasses during a day, which is on the left, and the daily composite of the ice concentration, which is on the right. So next, please. So besides the good spatial coverage shown in the previous slide, because of the high spatial resolution, the VIIRS ice concentration products shows detailed features of the sea ice. So the zoom in figure on the right clearly shows the sea ice leads, which are in a yellow color, long and narrow sea ice fractures being the sea ice leads. So next, please. Other than the ice concentration for individual overpass and for daily composite in the polar regions, we also generate the weekly and the monthly composite of ice concentration just to minimize the cloud cover impact, especially during the season when the cloud amount is really high. So for this year, Antarctic sea ice shrunk to below 2 million square kilometers this February, the lowest minimum extent since satellite records began 43 years ago. So the figure on the left shows our monthly VIIRS ice concentration in February this year. The figure on the right shows the monthly mean sea ice concentration from passive microwave. So they agree with each other really well in spatial coverage. The VIIRS ice concentration shows higher values than the passive microwave product. The difference we are still exploring, but it is known that in the melt season, like February Antarctic, the passive microwave products tends to underestimate the CS concentration because of the melting. Next, please. So the strength of the VIIRS S concentration is its high spatial resolution and high accuracy, especially in the melt season. And the strength of the passive microwave S concentration is its all-weather capability. So using the best linear unbiased estimator to blend, the blended product is an improved product with high spatial resolution and also under all weather conditions, as shown in the figure on the bottom. So we are routinely generating this blended S concentration product. So next, please. So we also produce the GOES-R S cover and S concentration products. This slide shows the GOES-16 and the GOES-17 ABI coverage. So the full disk scan is for every 10 minutes. The continental US corner scan indicated with the dashed line are every 5 minutes. And the two mesoscale scans indicated with the solid line are every 1 minute. So the nadir spatial resolution of the ABI channel is as high as 0.5 kilometers for ABI band 2, 1 kilometers for ABI bands 1, 3, and 5, and 2 kilometers for the remaining bands, including all the infrared bands. Because our GOES-R ABI-S products using the infrared bands, so the spatial resolution of the current ABI-S cover and S concentration products is 2 kilometers at nadir. Next, please. So the derived GOES-R ABI-S cover and S concentration provide a complete coverage of the area in the mid-latitude. So this slide shows a case over the Great Lakes on February 20, 2021. The figure on the left shows the GOES-16 true color image, and the figure on the right shows the derived S concentration. So by observing the figures, under the clear sky conditions, the GOES-R products do a good job in identifying S cover and retrieving S fraction over the Great Lakes. So again, we want to emphasize the quality of the cloud mask is very important to our products. So next, please. So with the high spatial resolution of the GOES-R data, the S cover and S concentration products can provide a detailed spatial information of the S cover. So this slide shows a case on Lake Erie on February 6th this year. The GOES-R S cover product locates the lake ice and open water near lake shore with high accuracy. The concentration product provides detailed subpixel S cover information. So next, please. Can you hit one more time for the animation? Yeah, thank you. But there are still potential for improvement. So the current GOES-R S products are generated every hour. The GOES-R data have higher temporal frequency, so it can provide more information. So for example, the GOES-R mesoscale scans provide information every 1 minute, as shown in this 1 minute animation of the GOES-16 true color image on February 14 this year. It shows the clouds. If you can please the animation one more time. Previous one, yeah. This is an animation to show the clouds are constantly moving over the Great Lakes region. The ice on the Lake Michigan, Lake Superior, and Lake Erie appear under clear sky with the moving clouds. So the data with high temporal frequency provides the possibility of a complete lake ice cover even with relatively high cloud amount because of the high temporal frequency. Next, please. So this slide further shows the derived ice concentration from GO-16 from 1500 to 2200 UTC on February 13 and 14, 2021. So the spatial coverage of the ice cover, the location of the ice cover are changing due to the cloud cover changes. So the combination of the products at different times can provide a more complete ice cover picture of the whole area. This shows the benefit of the high temporal frequency of the GOES-R data. Next, please. So this slide and the next one furtherly show the benefit of the high temporal frequency of the GOES-R data. So if you pay close attention, this slide shows a ship track on Lake Erie from a port in Ontario, then around Long Point on February 14, 2022. If you can please play the animation again. So you can see the ship track, yeah, on the top right corner of the animation. So with the data of high temporal frequency, we can clearly pinpoint the location of the ship. So if please go to the next slide. So this slide shows another ship track, if you can please the animation. So yeah, this ship leaves Cleveland on February 15, 2022. But we are currently looking at the ice products for these two cases to see if there is any noticeable change in lake ice properties before and after the pass of the ships. Next, please. All right, I will stop at the summary slide without reading all the points on this slide, and I welcome your questions and comments. Thank you very much.
All right, thank you, Yinghui, very much for that. And obviously, where we sit up here, for myself in my office at Lake Superior, we obviously make heavy use of this, and it's still very much winter outside my window. Just before we get into any discussion, just a reminder that a week from today, next Thursday, April 7th, same time, 12 Eastern, Dr. Yvonne Cesar, who is a physical scientist from the Environmental Modeling Branch of NESDIS STAR, will discuss VIIRS fire detection. And as always, you can contact Lee Byerly and Kashad Bowman on the TowerS team for any questions regarding the Satellite Book Club, the SBC, or any satellite configuration RPM stuff that you may have. So in the upper right-hand corner of your go-to screen is the chat window, and Lee has just dropped in there the feedback form. So be sure, if you have time, to fill that out. Drop your questions in there. I'll try to monitor those. And if you want to unmute yourself and ask a question, just let me know, and we will acknowledge you. So again, Yinghui, appreciate it, and we will we'll get into now the discussion session. Brian or Lee or Kashad, did you have anything else before?
Patrick, nothing from here at this point. I think we can get started with the questions. Encourage folks to put questions in the chat.
Sounds good. Very well. We have the first one in from Bill Soderberg. Have you found any new users as hopefully more people put these capabilities to use?
So I'm thinking we are working with the National Ice Center. They are routinely get our data and use our product in their CIS and lake ice analysis and forecast. So, and also we are working with the Alaska CIS desk and for their CIS monitoring and forecasting for the Arctic CIS and the CIS near the Alaskan regions. So the next step is to working with users to assimilate our ice products in the modeling. So by data assimilation, we are sure the forecast will be improved.
Excellent. Thank you, Bill, for the question, and Yinghui for the answer. I'll go to this one came in from Scott Lindstrom. Is there a difference in ice behavior over the freshwater of the Great Lakes versus, say, saltwater, say the Bering Sea for Alaska? So is there really a difference in the behavior that you see in these satellite products between fresh and saltwater?
I would say, like, for first, I think the lake ice, we all know that lake ice is mostly just seasonal ice. So it disappears at the end of the melt season and reappear again in the cold season. For the sea ice, it can be like a 1-year ice or multi-year ice, so that their spectral features can be different between the 1-year ice and the multi-year ice. So that may lead to some uncertainties in the reflectance features in the visible channel. That might lead to some uncertainties in the ice concentration. However, I would say for the ice detection and ice concentration retrievals, they are pretty much the same. However, the major difference is to retrieve the ice thickness. So the ice properties are different for lake ice and the sea ice. So that needs to be considered in retrieving the ice thickness. Thank you.
Excellent, thank you. This is more of a kind of a quick technical question. The approximate latitude above which the GOES satellite angle becomes problematic for detection and concentration products.
We look at the GOES-R ice cover, ice concentration, ice thickness products. In the mid-latitude, like Great Lakes, it performs really well. Like you said, the pixel size becomes larger with the higher latitude, but still we can see the ice detection and ice concentration retrievals performing pretty well up to even 60 or 70 degree latitude. We can see the CS cover just north of the Alaska region, so in the Beaufort and Chukchi Sea area.
Excellent. Questions keep coming here. You ready for another one, Yinghui? Here we go. This one comes in asking, have you considered a GO stereo ice product suite? So using both east and west simultaneously for the same target.
That's a good suggestion. Now, right now, we are producing the GOES-R as products separately for GOES 16 and 17. That's a really good suggestion to look at the same location, the ice products at the same location from GOES 16 and 17 and combine them together. We haven't done that, but I agree that's a really good suggestion. We will do that. We will look at that possibility. Thank you.
Oh, excellent. So any other questions? I'm looking at the chat and not seeing any. One that I have at Yinghui is especially related to the ice concentration and obviously the impacts on shipping. We had a large number of ships get caught stuck in the ice just outside and in Whitefish Bay and Lake Superior, literally just a few days ago. It was kind of a mess out there. The ice concentration products, in your sense, how, especially for the Great Lakes, I guess the maturity of the products, of, how accurate are they, and what are the kind of the challenges to really trying to improve that? Probably some of it is just validation of how thick the ice is actually out there, right? But kind of interested on your takes on especially the ice thickness, and with its impacts on shipping, and just where that is in development, and kind of what are the challenges or hopes for kind of breakthroughs.
Right. Thanks for the question. I think, yeah, I think for the shipping, both the ice concentration and ice thickness are very important information. So I would say for the ice concentration is pretty mature. It's well calibrated and validated, because we have some truth data from either from the passive microwave or from the sensors like Landsat 8 with very high spatial resolution. We can well calibrate and validate the ice concentration product. However, that's not the case for the ice thickness, especially over the Great Lake regions. I think there's more in-situ observations in the Arctic Ocean for the ice thickness, even though that's still limited. We have done extensive calibration validation of the VIIRS ice thickness over the Arctic Ocean. However, over the Great Lakes, there's not many in-situ measurements of the ice thickness. So we are still trying to validating and calibrating the ice thickness over the Great Lake regions, and trying to improve that retrieval based on the calibration and the validation results. I would say overall, the ice concentration is pretty mature and well calibrated and validated. The ice thickness over the Great Lakes needs more calibration and validation, or even improvement. Thank you.
Thank you. Looking in chat, Bob will confirm that is the best link. We'll move to Tim Schmidt's question. This one might need either Kashad or Lee to chime in on this one. And when will GOES ABI ice snow products show up in AWIPS, and are they currently in testing?
Thanks, Tim. That is a question I'm not sure about the response. So Lee, can you please address that?
Thanks,
if you
Yinghui.
can.
Yes, thanks, Yinghui. Thanks, Tim. The GOES ice products are in testing in AWIPS now. They're available. If anyone would like to see them, we have them available in a development environment in the cloud AWIPS. And they perform well with the GOES set of software, as do the other GOES products. They behave in that way, and Yinghui had shown a screenshot some slides back. We had a test flow of this data going last winter out to several sites, and there was a new update made to the algorithms, and a new release coming very soon. I think there's some decision points coming up in a few weeks, at which time the products can be considered by the National Weather Service for flowing out to sites by next winter. It depends on how the data flows are considered, whether it be over a satellite broadcast network or other means. But I would predict that they would be available in some form to offices next winter.
Excellent. Thank you, Lee, for providing the context on it. The next one from Brian. And he said you showed a Landsat ice image next to VIIRS, somewhere around slide 6. And he asks, if not already done, would it be beneficial, and if so, are there plans to include Landsat data into a multi-sensor ice product?
Yeah, thanks, Brian, for that question. actually, we have been thinking about this possibility. So so far we have collected Landsat 8 data for 4 years. We noticed the most of the Landsat data are on the coastal area, even in the Arctic Ocean. So there is very few scenes over the central Arctic Ocean. So that's limited the application of the Landsat data over the ocean. I'm not sure about that situation over the Great Lakes, but I suspect they are also just over the coastal area, not over the central part. So, but now we are considering the possibility to grabbing the Landsat 8 or even Landsat 9 data routinely from the USGS and considering the possibility to blending the Landsat 8 and 9 ICE products with our operational products. Yeah, because of the high spatial resolution of the Landsat 8 and Landsat 9. Yeah. Yep. Overall, so we are considering that possibility, and if the Landsat 8 or 9 data can provide more scenes over the central part of either the lake or the big lake or the Arctic Ocean, that would be provide more information and more useful. Thank you.
Kind of, I guess I have a follow-up on that one, Yinghui. One thing that we've really liked this year, and that NESDA set up a site for the SAR products. So both the winds and then I believe it's the normalized radar cross section. Is that something that can be in a multi-sensor approach also used in? The NRCS, those normalized radar cross section images are just so amazing for looking at the ice, especially when it's cloudy, and just the amount of detail. Is that something also that can kind of be fused in?
Yeah, exactly. I didn't mention the SAR ice products or SAR ice concentration in this talk, but we are routinely grabbing the SAR data from STAR. I think it's from STAR, and also we are talking with Sean Helfrich of STAR on the possibility to blending the SAR ice concentration or ice products with the VIIRS and passive microwave ice products. So I think the first step is to generate develop an algorithm to generate the SAR ice cover products. Then we can regrading the SAR ice cover product to the same resolution of VIIRS. Then we have a SAR ice concentration. Then we can blending the SAR ice concentration with VIIRS and passive microwave. That would be a very, very useful product because of the all-weather capability of SAR and also the high, very accurate ice cover and ice concentration product from SAR. So meanwhile, the VIIRS and the passive microwave can compensate the SAR's relatively low temporal frequency. So I think that's a great idea.
Excellent. All right, I think we'll take one more. And this one comes from Michael Laws, or at least Michael Lawson. Sorry, your last name got cut off in the chat. So how do these ice products handle very new ice, such as frazzle ice? These types of ice don't always show up very well in the visible or IR compared to SAR, synthetic aperture radar. And along the same lines, how well do these products do with water or ice that has kind of a liquid water coating on it? So I guess two parts. How is the handling of really new ice, and how is the handling of ice that maybe might have a liquid layer on top of it?
This is a really good question. Thanks, Mike, for the question. I think the new ice is really challenging for both the ice detection and ice concentration retrievals. just because they have really low reflectance, sometimes the reflectance close to the open water reflectance. So it's hard to detect. But we are thinking about just using the temperature test, because even very thin, very new ice can have the temperature lower than the melt point. So we tested some cases, and I think the temperature test works pretty well for detecting the new ice. For the concentration retrieval, I think if the new ice covers a large area, relatively large area, like a few hundred pixels, so we can use our ice concentration type point algorithm to retrieve the ice concentration really well. I wouldn't say it's perfect, but it's better than the passive microwave, because for those ice, I think sometimes the passive microwave also has difficulties in detecting and retrieving the ice concentration. For those ice, the passive microwave ice concentration tends to underestimate the ice concentration. So I want to say, like, we are still working on that. That's a challenge, but I think we will make progress soon. Thank you, Mike. If we make any, we can talk offline, like how we can improve on those situations. And if you have any good cases, please send to us. We can look at that more. Thank you, Mike.
All righty. Yinghui, you've taken on a lot of questions, and we appreciate it. So thank you for your time on that. I dumped in the chat a question I believe that Jordan Girth wanted to ask everyone, and that is, and you can just type in your answer in chat, and we can kind of just get a sense of everyone. And this is, he was wanting to know for the entire group, if a higher cadence is desired, would that be to see the, more of ice movement, to get more cloud-free scenes, or both? So that question is in chat, and you can feel free to type away your answer in there. Yinghui, I do not see any other questions for you. Appreciate your time answering all our questions and for your presentation. So I think with that's all I have. Brian, Lee, or Kushad, do you have anything to finally bring us home?
If nothing from here, we wanted to no more questions from here, and so we'll give folks just another second to make sure that we're not cutting anyone off. And if not, we're at 12:44. We've got a few extra minutes if there are any more questions. But if not, we wanted to thank our speaker today. Thank Yinghui for the informative presentation. Thanks, Patrick, for your facilitation. And if there's no further discussion or questions, we will look forward to seeing you a week from today for the VIIRS fire detection seminar that Patrick told us about. Any other closing thoughts?
I want to thank you again for the opportunity to present our work, and thank you all very much for your questions. Thank you.
Thank you, Yinghui. And with that, we'll wrap up the call then. Thank you.